And hello, everybody. Yeah, yeah, I think I was already introduced. So I've just wanted to present one of the work we have done to like we develop a methodology for real-time production scheduling, particularly for the case of thermoplastic industry. And this project, I should mention that has been a collaborative work with that industry partner. And the work that I'm presenting today is the work done by my former postdoctoral fellow, Dr. Majid Ghalib. So I need to acknowledge him here. So my presentation, I'm going to first provide a brief background of the problem under consideration, and then I will discuss about the proposed methodology, and then the case study and result will be discussed, and finally conclusions, future work. Like generally speaking, thermoplastic manufacturing is complicated and due to a variety of reasons. One of them is that like they are subject to receive high demand of volume of different type of products, different family of products, and they are always under constant pressure to reduce costs to remain competitive. And also sometimes from time to time, they are dealing with the lack of resource and supply. An example of that we have seen at the COVID era and even post-COVID, that automobile industry, they're dealing with the problem of shortage of chips, which it has impacted significantly their production. And also the machines that are being used for manufacturing, they are unrelated, and the preemption is allowed there. And also like when they wanted to produce different type of product family, they have to consider the setup times for that production. And another aspect of complexity is the machinery. They are subject to like they are highly maintained, means that in their production also preventive maintenance, which is mainly done based on the scale, time-based maintenance, need to also be taken into account. So having said that, so in general, like the production, thermoplastic manufacturing is the dynamic and has a stochastic nature. And this stochastic nature is mainly done due to some event that are happening at randomly at some unknown times. For example, arrival of the new order, the machine may break down, material shortage, and also like changes in the due date, which also changes the priority of the order to be processed. But most of the manufacturing now, they're considering switching to a smart manufacturing, and they're trying to implement and adopt the newer technologies such as Industry 4.0, which also has been the case for the manufacturer that we work with. And but in this case, they are like most of the decisions that they are making, they need to be made in real time and including the production and scheduling. So it means that like we have to develop methodologies to be able to rapidly respond to any event that takes place and have the optimal reschedule plan ready to be implemented. And so considering all the conditions, we can classify thermoplastic manufacturing scheduling problem to an unrelated parallel machine scheduling problem, but with some consideration, which includes batch processing because products are produced in batches, preemption, safety stock, and dedicated machine and sequence dependent family setup. So if this type of problem, which can shortly call it as UPMS, it's a combinatorial optimization problem, which is very strong NP hard. But how manufacturing process actually trying to perform real-time scheduling their setting, most of the time, including our industry collaborator, they are employing some sort of dispatching rules, which dispatching rules, even though they might be simple, but in the case of rescheduling, like not necessarily result in the optimal or even near optimal solution, because like whatever has caused the interruption to production, they may vary, and then depending on the type of interruption, not necessarily always following a specific dispatching rule can result, can give us a proper result or optimal solution. Another alternative would be utilizing meta-heuristic that, of course, they can provide like higher quality solution and more robust solution. But the problem with meta-heuristic also is the increased complexity and computational time when we go to real world setting, we are dealing with a large number of machine and larger product to be scheduled in the machine. And as an alternative for this like tool, now we can see the shift towards the utilization of like developing reinforcement learning based methods, in which both dispatching rules and machine learning have been combined. But even with this case of methodology, there are still challenges we need to overcome. And these challenges include, for example, like effectiveness and scalability of the algorithm, and mainly because reinforcement learning requires that states and action to be identified. And when we are dealing with a large states and large action space, so this means that like these algorithms, they may no longer be effective, or we cannot, like they are not scalable. We cannot go to a large real size problems. And another issue that we need to overcome to that is the design of reward function and also learning algorithm, because both of them significantly impact the optimal solution. And some other limiting aspect would be the constraint of the real-time environment, such as the condition that I already mentioned them we are dealing with in this case of the for our problem. So for doing that, like we are proposing to a use of deep Q network and also model-based policy algorithm. And these are being used in an agent-based system. And we are utilizing these two mainly because we also want to compare like how a model-based can perform against a model-free model algorithm, and then to be able to compare that. But that's generally our solution methodology, which I'm going to explain in details in the next slides. But before that, because like the basis of all of these methods are reinforcement learning, so just a brief introduction to like how an agents perform in a reinforcement learning setup. So in a reinforcement learning setup, we have an agent which is interacting with environment. Environment provides information to agent, which is information mainly they are in the form of observation that also is defined as states. And agents, depending on the states, observed states, it's taken action, and then the action is being received by environment and then being implemented. And depending on the outcome, the action, and how this outcome is close or far from the intended objective of the task, then a reward is given to the agent, and then agent like learn that way. So it means that agent consists of has two components. One of them is the policy, which is the set of rules that are being used for decision making. Another is the machine learning and RL-based algorithm, which in fact used to update the policy on a continuous basis. So this is what it does. So like means that this RL algorithm continually update the policy based on the new information which is received in form of action, observation, and rewards. And this learning continues until like eventually the optimal set of action eventually selected, which this optimal set of action is the ones that result in the maximum sum of rewards. And in most of this reinforcement learning, the algorithm is an unsupervised one because like an agent is expected maybe to work in some unknown environment, and then may need to select an action dealing with an unobserved event which hasn't been trained for before. And like here shows the like general structure of our methodology. So it starts with the step one. It consists of 5 steps. So step one is the formulating the problem, and then step 2 like creating environment. Step 3 is the creating agent and training agent and validating agent, deploying the policy, and then evaluation, which this one is like an iterative procedure. Means that like if the final policy or performance is not satisfactory, we have to come back to again revise maybe the state's action, or like we again in fact we need to come back and review everything from step 2. So I'm going to go a little bit, provide more detail about each of these steps in the next slide. So of course, like we have to formulate the problem. Formulation of the problem is basically like the providing a mathematical formulation of the production scheduling, which in fact means that stating the assumption which we have here. We are assuming that we are having n product that belong to different families of product, and these product belonging to different families of product need to be scheduled or need to be assigned to different machines, which we are assuming that there are M hydraulic press machines in that case study, and the machines have different sizes and tonnages. And then we also assume that product arrive randomly and they need to be processed in batches, and the batch size is determined based on the demand and also based on hand inventory and the amount of safety stock to be produced. The safety stock is usually the amount of the product that they have to be produced in advance, and just to make sure that if production is down for any reason, they already have enough product on hand to meet the demand. And usually in practice, a minimum maximum is considered for different type of product, which in our case like is 3 and 5 years respectively is considered the safety stock. And one constraint, which is a machine eligibility constraint, need to be considered here, because different product need to be, they need for the production different tonnages is used. So it means that this add the constraint that the machine, not all the machine cannot process all the products. So they like certain number of machines, they can process every type of jobs. And as I mentioned also in this problem, we are assuming the product family requires setup times. So because like for any product family, a specific mold is required to be put on a machine. So we have to consider this sequence dependent family setup time. And continuing with the assumption, we also assume that each mold has a set of cavities, and the number of cavities obviously depends on this mold and the machine size. And each machine press, at each machine press, the mold produces a number of products, which is the same as the size of the cavity, so the number of cavities on the machine, on the mold. And also we define the cycle time, which is the cycle time is required to be calculated, which is the time between the machine presses. So the processing time also are determined based on the selected machine cycle time, batch size, and number of mold cavities. We are assuming that demands have shipment days, and these demands, the shipment days are considered as the due days in the problem. And we also assume that all molds and the machines are ready and available at time 0 at the beginning of the production scheduling. And we also assume that transportation times are negligible. So these are the key assumptions for describing that production environment. And then the decision that we wanted to optimize is just a decision about the assignment of the job to the machine. So these variables are 1 and 0, like if a specific job is assigned to a specific machine, and the batch sequencing, which take care of the like if an order precedes another order. So this sequence is determined using this variable, and the batch size variable for the batch size and safety stock. So these are the variables we would like to optimize. And the problem is formulated as a mixed integer linear programming model, and with the objective of minimizing the total cost. And the total cost consists of the cost of tardiness and the machine setup cost, which we wanted to minimize. So obviously, like all the mixed integer programming model, the model is subject to certain constraints. So we have a different set of constraints defined. So for example, this set that we can see, they are taking care of the eligibility of the machines, means that they're taking care that like if a product needs a specific tonnage size, it should be dedicated only to those machines that they have that size, and also make sure that each job is assigned to only one machine, a specific machine. And this set of the constraint they are calculating, obtaining the processing time, size of the batches, and the amount of the safety stock. And this set, they are making sure, like they're considering for the starting time of the job. So they're making sure that like the job starts when a job can start when the job is there. Like the starting time cannot be they cannot be started when the job is not there. And also this one is used for the case that the job can start if a machine is available, or if the machine comes back from passes its recovery time, if for example, it has been down for maintenance. And this set of job taking care of that, like the preceding jobs, means that they are making sure if one order precedes the other, like all of those orders, they are allocated and assigned to the same machine. And finally, like this set of constraints, they are taking care of the completion time, because completion time, make sure the completion time is minimum or greater than equal or greater than the start time and the processing time. And the tardiness is a difference between completion time and the due date, with the exclusion of the time required for the producing safety stock. And this optimization for to solve that optimization model, like an optimization module is developed, which is based on the simulated annealing. And so for that, this optimization module consists of 3 components: a solution representation, neighborhood structure, and decoding mechanism. Which for solution representation, of course, like we should have a flexible solution, which is also simple to be evaluated. And for that purpose, what we proposed was a solution structure consists of 5 parts. So the first part is the vector, like each part is a vector of size n. So the first vector is express the status of order, which the order can have for statuses. One is represent the case of order waiting for processing. 2 shows completed orders, 3 order under processing, and 4 interrupted order. And the second part of the solution structure contains the job assigned to the order, the machine that the job order is allocated assigned to it. And the third part features the order sequence, so it means that like it has the rank of the order on the same orders on the same machine. And the last 2 parts of the solution structure represent the safety stock and batch size. So if you wanted to graphically represent this solution, these are just shows the graphical representation of the solution structure, which, as I said, has vector of 5 vectors of size n. And then for the generating in the simulation annealing, we need to generate neighborhood solutions. So for generating the solutions, we use different operator for each part, depending on because they vary, so different type of operator be used. So for example, for part 2, which is machine assignment, the operator just randomly selects some of these machines from some of the elements from this vector and randomly just changes the order allocated to them. And or for example, for the order sequence, a linear operator has been used, which again some random sequence are being selected and then the sequence being changed. And when we have that, like after that, from the solution presented in the form of this solution structure, when we have all of these components, all of the information like part 2, part 3, and 4, and 5, so the solution can be evaluated. And because of all the formula we develop, for example, for calculation of the processing time, and which I showed in the previous slides. So it means that we can calculate with having the solution, one solution in hand, processing time, starting time, completion time, tardiness value, and objective function all can be calculated. And then we go like to the step 2, which is the creating environment, and we wanted to like which in our case study, the environment is the models the task of machine assignment and order sequence. This is the task that's going to be accomplished, and with the consideration of those specific condition that the production has. And at each decision point, like any typical RL-based setup, at each decision point, the agent gets the current state from the shop floor. And then the agent selects an action based on the received state, and the environment receives the action and schedule the selected order on the assigned machine, simulate the production, the scheduling process on the partial sequence. And the agent then receives the subsequent state and the corresponding reward from the environment. And this process continues until all of the orders are scheduled, and in that case, simulation terminates. And as a part of creating environment, we need to define a state space. And generally, like in reinforcement learning, the space is used to as some features that describe the changing in the environment. And some of the examples that usually being used and utilized as a state is for example, the number of available machines at any time, and or like the remaining job that still need to be processed. For example, if interruption happens and some of certain jobs hasn't been yet processed, so like these are considered as features. But the problem with like this selection of features is that like when we are dealing with like when the number of machines increases or the number of orders to be processed increases, the problem sizes get very big, and so we cannot expect to have a satisfying result. There will be a lot of variation, for example, in the agent output. So and another problem would be that if we do that, like not like in a production setting, we may not have many different scenarios, like only the scenarios that we use for training. So the agent is only trained for those scenarios. So if it encounters an untrained scenario, also like the performance of the agent will remain in question. So to avoid all of these, one possibility would be to come up with a generic state feature. And this generic state feature is the one that is independent of the specific problem under consideration. Is an independent of the, for example, problem size, and that makes it scalable. And so this means that instead of like considering let's say the number of available job and the remaining job to be processed as the state, so we propose to use 10 generic and normalized state features, which they are being used in both agents that we develop. These are the features that we consider, so which I'm gonna just read them: average machine utilization, standard deviation of machine utilization, machine availability rate, average stock coverage percentage, standard deviation of stock coverage percentage, accomplishment rate, percentage of remaining workload, order setup rate, tardy orders rate, and non-tardy order rate, which all of this allows the methodology to be applied to any size problem. So we are not limited, I mean, to one specific. Means that the model is not just applicable to certain environment in which the model has been trained. And then another decision that need to be made is the defining action space. And then again, when we are dealing with a larger scale, again, depends on the problem size. We are having different kind of problem. One of them would that we need to do retraining every time that we are solving a problem with different number of jobs and machines. Again, retraining is required every time that a new event takes place, and also training is required at each rescheduling point, because at every rescheduling point, different number of available machine and remaining number of orders to be processed, we are dealing with that scenario. And this also causes infeasible actions, which also we don't want to do that. I mean, it would be really time consuming and not effective. So for having said that, and to avoid that problem, what we are proposing to use like the action that the agent, limit the action that the agent need to select from. So here the action only needs to decide about the proper order and the machine that the order need to be assigned to. And this action also even can action space can also even be reduced by only selecting the product family. So at the end means that like what we are proposing, only like either no product family is selected to be assigned to a specific machine, or like the decision would be only reduced to selection of product family to be assigned to a machine. So we need also to define the reward function, and reward function, because an agent modifies its policy during training based on the reward function for various state action combinations. So reward function has a significant impact on the convergence of the agent. So for our case, what we consider 3 state features at the current state and next state for the design of the reward. And these are, which includes tardy orders rate, order setup rate, and average utilization. But in addition, we also incorporate an upper bound on the optimal solution, which is obtained using the developed simulated annealing optimizer, which can improve the searching effectiveness and efficiency during the training process. And so 2 agents has been developed. For one of them is DQN agent, which is an online model-free and off-policy reinforcement learning technique, which in the online means that the learning done in an online mode by interaction with the environment is model-free, because like it doesn't assume any modeling behind, and it's off-policy means that it for decision-making utilize all the policies that have been used and developed by interaction with the environment. And also DQN agent is a value-based reinforcement learning that is able to train the policy to approximate future reward. And our DQN in fact, the structure of that is the architecture of that is a deep neural network, which consists of 7 fully connected layers with 1 input, 1 output, and 5 hidden layers. And again, we incorporated an upper bound using that simulated annealing optimizer to, again, be able to improve the searching effectiveness and efficiency during the training process. And the number of nodes belonging to the input and output layer also are the same as the number of state features and available actions. So for the exploration in done by DQN agents, so the exploration of the action extent, we employed epsilon greedy exploration, and also we employed a double Q network. So when training is done, during this training, the DQN agent also the policy properties at each time step. Each time step in our problem is when an event takes place, could be machine breakdown, new job arrival, or like a machine is recovered, or a batch is completed. And here it shows the framework of the DQN training process. And we also employed another agent, which is a model-based policy optimization, which is online off-policy reinforcement learning algorithm, in order to be able to compare the model-based versus a model-free policy. In a model-based, in fact, the decision-making is done, like an optimized decision is done using the predictive model, means that like the action is decided based on the model, thinking about, okay, what will happen if a certain action is taken. But model free doesn't have that, means that learning done directly with interaction of the agent with environment. So we wanted to do that. And what this model-based policy optimization does is does training. During the training, the agent updates the environment model at the beginning of each time stamp, and then use the train environment model. The agent generates some samples, and then the samples are then stored in a circular experience buffer. But in addition to these generated samples, also there is also another storage for the sample that coming from a direct interaction of the agent with the environment. So eventually both of these are used for like for the updating the policies. And then then we have the policy deployment. So the policy that comes from these two agents eventually need to be implemented, and then the performance need to be evaluated which is in step 5. But we have to also consider that this policy also can be updated whenever we need to do training the agent on new events, and also because I mean, it doesn't really require new training, but the policy can be updated. Means that if the agent observe a new event that hasn't been trained before, then they can learn from that, and then they can update the policy on a continuous basis. And then the evaluation, which can be done, and then overall numerous production condition can be created using the simulator model, and then overall those one that can be kept, because those one that result in the minimum overall cost. And what comes from the output of this model, this model propose the optimal policy, optimal, for example, rescheduling at any event time, but this one also can be provided to the scheduler on site, and then because that person can also take his or her experience into account, and then decide whether they want to adopt that optimal solution or not. So means that it doesn't need to rescheduling can be done in a automatically being applied, implemented. So as a case study, we consider the data, the parameters of this case study comes from that real case, which comes from the that collaborative project we did with industry partner. So it is learned that the best way is to scenario being generated based on two features. One of them is the number of the family numbers and of the product, the number of family products, and also the number of machines. So we consider different scenario, for example, 5 family machine with 5 family of product with 11 machines, and then with different tonnage or sizes, cost of the setup, cost of the mold, and also different order number, and different features or parameters of the environment. And we assume here that the arrival rate of the product, they are random, and they're following Poisson process with these rates. And these are the data being used for training, but for the testing similar setting, the difference is that the order number has been generated randomly, and also the arrival rate, they are random, not following these parameters. And then, but like all the algorithm, so we need to do tuning of the parameter or hyper parameters. So this table showing the the final parameters being used in the SA optimizer, and also the parameters of the DQN agent, as well as parameters of the MBPO agent. And but we wanted to compare the performance of our proposed methodology with some of the benchmarks. So we use both dispatching rules and knowledge-based rules for that purpose. From the dispatching rules, 6 different rules being considered. For example, FIFO, which is select order with minimum arrival time, or SPT, which is the select order with the shortest processing time. So we wanted to see how our model perform in comparison with these rules, and also for the knowledge-based approach, supervised classification model was trained using these 4 algorithm, decision tree, random forest, and SVM, and artificial neural network. And for the training data, like the training data for these models is labeled using the best dispatching rule used in the training scenario for the 6 rules that I said in the 6 dispatching rules. And so this means that we are dealing with 6 classes of the label. And for all benchmark approaches, which includes dispatching rules and knowledge-based approach, the same feature as DRL agent have been used. And the training data is labeled using dispatching rule with the best total cost value. And hyperparameters of the used knowledge-based approach also to tune using the k-fold cross-validation mechanism. And here are the results that we obtained. So this one shows compares the output of this methodology and methods based on average relative percentage deviation. Means that because here the objective is to minimize cost, so the cost from each of these methodologies compared, and then the cost of each method and the best has been calculated, and then the deviation from this, like the relative ratio, means that the cost obtained from the methodology minus the best cost divided by cost. These are all calculated as a RPD. And so as we can see, for different consider scenario, for example, we have 5 product family and 11 machines. You can see that DQN and the proposed DQN and MBP, they are outperforming the other algorithms. And so this is another scenario, like with 7 product family and 21 machines. So again, these are performing much better than the other, like the existing methods, especially for real-time production and scheduling in real settings. So as conclusion, like the main contribution of this work has been on the proposing a methodology which can overcome the limitation of the classical optimization method, particularly proposing a method that doesn't depend on the size of the problem or the number of machines or the number of orders to be processed. So it's scalable, can be applied in different scenarios and in different settings, and without being required to do retraining, and even without like retraining in the case of observing an unexpected events. And yeah, because mainly this is done because of the employing a generic state and action representation, which have been independent of the problem size. And also another novel aspect of the work was the employing a reward function that in which an upper bound has been imposed in order to improve the performance and enhance the search during the training stage. And yeah, I mean, and the model has been able to achieve comparable results and realize adaptive and real-time production scheduling that we showed that. And in fact, this methodology is now being utilized by our industry partner. And as the future work, what can be done as an extension of the work, one of them would be that considering the same methodology for different other environments, such as like a flow shop or job shop, and considering additional considering, for example, in this case, we didn't consider preventive maintenance. I didn't assume that machine may not be available for conducting preventive maintenance certain times. The model can be extended to that. And another aspect would be using of more advanced deep learning reinforcement learning techniques, such as actor critic or hierarchical reinforcement learning, or considering of multi-objective optimization when, for example, we wanted to minimize make span at the same time, reduce tardiness at the same time. And another interesting aspect for the extension of the work would be the use of explainable AI technique, because to especially see that like how industry would like, I mean, they would like to utilize and trust such system in real world setting. Yeah, thank you very much. I think it was 45 minutes, 46 minutes. So thank you very much for listening to this presentation. Yeah.